Check out this cool experiment we did a while back. I take some red color solution, put it in a transparent solution, and it becomes blue. What's going on? That's not it. Now I take a blue solution, put it in a transparent solution, and it turns red. Again, it looks like magic. It's not magic, it's the chemistry of acids and bases. And that's what we're going to explore in this video. So let's begin. So, what exactly are acids and bases? Well, if you look at their most primitive definition, it was based on their tastes. Well, acids are usually sour tasting and they can be sticky. In fact, the word acid actually comes from the Latin acidus, which means sour. And some of the most common examples you can think of are lemon juice, which contains citric acid, vinegar, coffee, soft drinks with soda in them. Yeah, they're all acids. Okay. What about bases? Well, turns out bases are bitter tasting and they're quite slippery. And again, common examples would be soaps. If you've had soap water gone into your mouth, you've probably tasted bases and you probably know that they are bitter. If you've tasted stuff with too much baking soda in them, well, they taste bitter. Well, because bases taste bitter. Other examples include detergents, antacids, and so on. But of course, this is not a great definition of acids and bases. There could be so many other things that are sour or bitter, which may not be acids or bases. So, can we come up with a more concrete definition? Well, turns out there are more than one ways to define acids and bases, but we're going to start simple. We're going to use what we call the Arrhenius definition or the Arrhenius model of thinking about acids or bases. In this particular definition, we basically say acids are things that give you H plus ions in aqueous solutions. And similarly, bases are things that give you OH minus ions in aqueous solutions. In other words, if you mix something in water and it starts giving you H plus ions, these are acids. And if you mix things in water that gives you OH minus ions, well, those are bases. So let's take an example. If you take HCl in an aqueous medium, what you will find is that HCl will dissociate into H plus ions and Cl minus ions. Now, since we got H plus ions on mixing HCl in water, HCl is an acid, and you probably know about this as a hydrochloric acid. Another example could be this is called the acetic acid, and if you mix it in water again, you'll get some H plus ions. So this is also an acid. Similarly, let's take some example of bases. If you take sodium hydroxide or potassium hydroxide, mix them in water, take a solution, aqueous solution of them, you will find sodium solution, sodium ions, potassium ions, and OH minus ions over here. So since they give you OH minus ions, they are bases. Now, when we look at this, it might be reasonable to think that all bases should have OH in their formula, right? Otherwise, how else will you get OH minus ions when you put them in water, right? Well, turns out that's not true. For example, if you take ammonia and put it in water, that will also increase the amount of OH minus ions, which means technically ammonia is also a base. But it's not so straightforward to identify it as a base. Looking at it, we'll not be able to tell it's a base just by looking at Arrhenius definitions, right? This is the reason why we have other definitions. Otherwise, how else will you get OH minus ions when you put them in water, right? Well, turns out that's not true. For example, if you take ammonia and put it in water, that will also increase the amount of OH minus ions, which means technically ammonia is also a base. But it's not so straightforward to identify it as a base. Looking at it, we'll not be able to tell it's a base just by looking at Arrhenius definitions, right? This is the reason why we have other definitions of acids and bases as well. But for the purpose of this video, let's not worry too much about it. Let's just stick to Arrhenius, because guess what? Even with this Arrhenius definition, it has a lot of explanatory power. We can understand a lot about acids and bases. For example, you probably know that acids are corrosive. They can corrode metals and they can also erode stones. This is why acid rains that you get due to pollution can also damage monuments. But why does it happen? Well, a simplified explanation could be that the hydrogen ion that is formed from the acids, well, that can suck electrons from the metals. In doing so, hydrogen gas is formed and that gets released and that causes that hissing sound. And now the metal ion that is formed, a positive ion that is formed because it has lost electron, can actually bond with this anion over here. And that molecule now can actually dissolve in solution, and that's how metals can get corroded. Something similar will happen with your stones as well. So the culprit is the H plus ions. Okay, what about bases? Well, bases have the ability to break oil or grease, and that's the reason why they're used in soaps. But again, how does that happen? And again, an oversimplified explanation over here would be usually oil or grease, they do not like water. So they do not dissolve in water. That's why you cannot use water to wash them off. But OH minus ions, what they do is when they attach to oil and grease, they make them water soluble. And so in the presence of a base, oils and grease can dissolve in water and you can wash them away. Amazing, isn't it? But wait, there's more that we can explain. What would happen if you were to mix acid and a base? Well, again, let's look at it. If you mix HCl with, say, NaOH, well, H plus, the positive can attach to OH minus, and you get what? H2O, water. And Cl minus will attach with Na plus NaCl. Hey, we'll get a salt. Which means when you mix acid and a base, you will get a salt, an ionic salt, and water. This is what we call the neutralization reaction. And this is why we say acids and bases neutralize each other. So in a neutralization reaction, when you mix acid and a base, you'll always get an ionic salt and water. And just like how when magnets stick to each other, they release energy, when these ions and these molecules stick to each other, they release energy, meaning neutralization reactions are always exothermic reaction. They release energy, meaning neutralization reaction, when you mix acid and a base, you'll always get an ionic salt and water. And just like how when magnets stick to each other, they release energy, when these ions and these molecules stick to each other, they release energy, meaning neutralization reactions are always exothermic reaction. But wait, there are more properties that we can explain. For example, if you look at these solutions, acidic or basic solutions, do you think they conduct electricity? What do you think? Well, guess what? We have ions, right? When you have them in solutions, this means we have electrolytes. That means they do conduct electricity. So both acids and bases can conduct electricity. And guess what? It's the H plus ions that actually causes acids to taste sour, and it's OH minus ions that actually causes the bases to be bitter. It's got something to do with how our taste receptors work and everything. But what I find incredible is that just by looking at this one definition, there's so much we can understand and so much we can explain. And by the way, now that we know what acids and bases are, instead of having to taste them, which we should never try doing it in a lab, it's a very dangerous way to try and identify acids and bases. We can create solutions that change colors depending on whether they are in an acidic medium or basic medium. One such indicator is what we call a litmus solution. And that's what we saw at the beginning of the video. So this is the litmus solutions. These are made by extracting dyes from lichens, which are interesting types of organisms. Anyways, they usually come in two colors. We have the blue litmus solution and the red litmus solution. And the reason we have these two colors is because acids turn blue litmus to red. Again, this has something to do with the H plus ions. They react with the blue litmus solution, they change their properties, and as a result, the kind of color they absorb from the light that changes, and that's the reason why it starts showing red in color. It's amazing if you think about it. And bases do the other way around. Bases turn red litmus to blue. And if you find it hard to remember, I used to find it hard to remember, well, a simpler way to think about it is acids turn litmus to red, bases turn litmus to blue. Bases to blue. That's how I remember. So acids will turn things to red. Okay, so now let's add the litmus solution and see what we get. So here we are adding red litmus. And look, the color is changing to blue. So that means this is a basic solution. So this is a base. So that's what we saw earlier. And similarly, if you now take blue litmus solution and add it over here, look, it's changing color to red. What changes color to red? Well, it's an acid. So this is an acid. So this is how we no longer need to use our tongues. We can use litmus solutions to identify whether we're dealing with bases or acids. But of course, it does not tell you how basic or how acidic is it. Is it very acidic? Is it very basic? It doesn't tell you the pH. And for that, we have better indicators. Like we have pH indicators, we have pH sensors, and all that good stuff. This brings us to the last part, which is my favorite part, that is thinking about the strength of the acids. You probably know certain acids, like say citric acid or vinegar, they're not very harmful. You can taste them, and we probably taste them on a daily basis. But what about hydrochloric acid? Oh, that can be very harmful. Same is the case with bases. Certain bases can be very harmful. Why is that the case? Well, that's got something to do with the strength. Well, what does that mean? Well, let's see. If you look at an acid, a generic acid can be written as HA, Well, in aqueous medium, it gives you H plus ions. That's what makes it an acid, and some anions, which is A minus ions over here. Now, when I dissolve this in water, there are two cases that we can see, and I want you to think about what the difference between them is. Okay, this is case number one. Sorry, this is case number one, and here is case number two. What difference do you find between them? Well, in the first one, you find 100% of all the HA molecules have dissociated. There are four I have shown over here, and all four are dissociated. Such acids are called strong acids. When you have 100% dissociation, almost all of them get dissociated. We call them strong acids. Your hydrochloric acid, sulfuric acid, nitric acid, they're all strong acids. Same is the case with base. When bases have complete dissociation, we call them very strong bases. But what's happening over here? Well, here also I have four HA molecules, acidic molecules, but only one of them have dissociated. In other words, partial dissociation. Whenever acids undergo partial dissociation, we call them weak acids. And your citric acid, carbonic acid, phosphoric acid, they're all weak acids. And by the way, these are the acids that you find in your soft drinks. Now, here's the cool thing. I can increase the concentration of it. See, currently the concentration is the same, right? Like you can imagine this is 1 liter. I have 4 molecules per liter here. I have 4 molecules per liter over here, just taking simple numbers. But what if I had added more molecules over here? I add more molecules over here. Look, I have made this more concentrated. So this now has become a more concentrated solution compared to this one. This is compared to this one more diluted, right? So notice I can have a concentrated weak acid, but even in that case, I will see because it's very partially dissociating, the dissociation percentage is usually around 5-6% or something, I won't have a lot of H plus ions over there. So nothing much is going to happen. It's not that harmful. But in strong acids, even if it's diluted, I can have a lot of H plus ions because 100% dissociation happens. Now imagine, what if I had concentrated strong acids? Oh, you'll have a lot of H plus ions and you probably want to stay away from them. So this is why these acids can be super dangerous if they are if they are very concentrated. So you can see the strength is a measure of how much they dissociate. 100% dissociation, strong. Partial dissociation, weak. But remember, concentration is how much amount of, acidic molecules you have. If you have a lot of them per liter, say, very concentrated. If you have a little bit of them, less concentrated or diluted. And finally, if you're thinking about weak bases, bases are slightly more complicated, and so we'll not talk too much about them.
Okay, guys. I'm gonna end it there. Um, if you, I don't think anyone really watched this, but if you did watch this later, uh, thank you. Well, I'll stretch my face.